So this session is on actually basically okay. So it is the introduction to GEE. GEE basically means the Google Earth Engine and its application in developing the cloud-based rainfall runoff model. So initially, the first of all, we will start with the hydrological cycle. So those who are in the field of hydrology or water resources or studied some bit, so they are very much familiar with this picture that how the hydrology works. That means from which point the water comes and from which point the water goes out from the ecosystem, and how it revolves within the ecosystem. Like as we see that we get the huge amount of water through the precipitation, also known as rainfall, and small amount of the precipitation will go as an evaporation, or some amount of that precipitation comes in the form of snowfall. And so these are some related terminology in the field of hydrological cycle, that how the water enters and how the water exits in the different forms. So there are the first question that arises in our mind, that why do we need any type of hydrological modeling? That why do we are supposed to do any type of hydrological modeling? First of all, the river basin modeling is very complex. The river basin hydrology is very much complex, and it's mainly depend on its basin characteristics and surrounding climate. So to understand the hydrological process, we need to do some type of modeling. To estimate the individual hydrological component, we do that. To generate the scenarios with respect to land use changes and climate changes, and to manage the water resources for the benefit of mankind. So suppose if you want to build a dam, it's just a very basic idea of any hydrology or water resources field. So in order to build a dam or a reservoir, we should have a proper understanding or a proper evaluation of how much amount of water is entering to that particular ecosystem, or that particular outlet, or to that reservoir. So for that purpose, in order to estimate that particular amount, we generally do the hydrological modeling. So when we talk about the hydrological modeling, it is not only about the runoff or the rainfall. It is about all the parameters that are present in the form of water, either through precipitation, or we need to get the storage abstraction, that how much amount of water is actually going to the groundwater or infiltrating, then the amount of evaporation, evapotranspiration, which is very much useful in the evaluating crop water demand. Then we have soil moisture accounting, then we can do runoff production. We can get the snow melt runoff, because in the hilly region, like the Himalayan region, all the Himalayan rivers like Ganga, Brahmaputra, they not only get the water from precipitation and base flow, sorry, but they also do get the water from the snow melt and glacier melt, then runoff routing, channel flow routing, groundwater flow, and the water quality modeling also. So there are n number of things that can be done within this hydrological cycle. So presently we are talking about the hydrological model. So from very beginning to at the latest stage, we have seen various amount of advancement in the field of hydrological modeling. So as we talk about the very first, or in the earlier days, what was happen, or what the analytical approach that the previous people adopted to model the hydrological cycle. So initially in 1872, a Binny's table is get introduced, and it is one of the oldest documented rainfall runoff relationship that developed in 1872 for specifically Indian watershed. After that, the Burlow's table invented in 1912. After that, some of the similar approaches, just like strength tables, English formula, D'Souza formula, Kosler formula. So all these are developed in estimating the rainfall and runoff relationship. So in all of these equations, or in all of these formulas, we get a simply give the amount of rainfall as an input, and we get the amount of runoff as the output. But later on, at the later stages, some of the agencies and some of the ideas came up that why include only the amount of rainfall? Why not we use the land use land cover? Why not we include the soil moisture? Why not we include some other parameter in generating the runoff? So on that basis, in 1933, organization named Soil Conservation Services performed. It is an US-based organization, and in this organization, in 40s, Sherman, a scientist, has proposed that there is a definite relationship between rainfall and a runoff by a unit hydrograph theory. So later on, the Mokas suggested to include certain parameters like land use, land cover, soil moisture, or what you can say soil type, soil texture, antecedent rainfall, and the spatial distribution of rainfall in estimating the surface runoff. And based on the infiltration rate, Musgrove and other scientists group the soil into the 4 classes. And after each of these evaluation steps, we get a technique known as SCS curve number technique. So these techniques actually develop on the basis of all these parameters. That first of all, we include the rainfall, then we include the land use land cover, we include the antecedent rainfall, soil texture, etc., in order to get rainfall runoff model. So why we are talking about the SCS curve number? Because this is the technology that is widely used in the field of hydrological domain. Various advanced hydrological model, either HEC HMS or SWOT model. So most of the advanced hydrological model adopt the basic soil conservation SCS curve number technique. So it is a very very complex number of methods. It totally depends on the curve number, and it is developed by the Natural Resource Conservation Service method. So it is a very widely used method in the field of hydrology. It accounts for the effects of soil properties, its lands cover and antecedent moisture, and the prediction of storm flow depends on the total runoff there rather than the intensity, because most of the models or most of the techniques are depend on the rainfall intensity, but this model is depend on the total amount of rainfall, not the intensity. And it is based on a very simple and conceptual model. So this is the simple formula that were adopted in calculating the amount of runoff using the rainfall. So this is the formula in which actual retention is equal to P minus IA minus Q. And we will just talk about in the next slide what is actually P and what is IA and what is potential retention. So generally Q is the discharge, which is the our ultimate output. P is the precipitation, IA is the initial abstraction, and S is the maximum potential retention. So IA, that means initial abstraction, means when the water will fall on over a ground. So some amount of water will infiltrate downwards, and it totally depends on the LULC, that means land use, land cover, and soil type. So inclusive of these parameters will definitely generate a IA and S for that particular ground. And on that basis, the final equation come up as discharge is equal to P minus P is nothing but the precipitation minus 0.2S and the precipitation plus 0.88S. And where the S is depend on the curve number. And this is the formula for the S. And so ultimately we get the one thing that curve number is a function of land use and soil growth. So if land use or soil is changing, curve number will change. If the curve number will change, the S will change. And if the S will change for the same precipitation, the runoff will definitely change. So if you look for any type of literature survey, if you do thoroughly literature survey, so you will get n number of documents which will define the various type of curve number for different land use and hydrological cycle. So in this method, the soil is divided actually in the 4 group A, B, C, D, where A denotes which has a maximum amount of water retention, that means minimum amount of runoff, and D denote the soil which has a maximum amount of runoff and least amount of initial abstraction. And when there is a feature or there is a field area in which different type of land use land cover are there and different type of soil groups are there, so different type of curve number will definitely be there, and you can get this curve number from different type of documentation or literature. So these are just an example of the agency which has developed the curve number technique. For example, if there is a either we can say a scrub forest. Okay, so in the scrub forest, if the soil group is A, and the curve, then the curve number will be 33. So if the curve number is less, that means it will have a very less amount of runoffs. And when we go to the this particular land use land cover, that scrub forest, and when we see this particular land cover in the D group, then we can get some high amount of curve number. It denotes that most amount of water will be part of the runoff. That means it will be less amount of water stored in a ground or will go as an initial expression. So this type of curve number is main deriving factor of runoff in this particular method. So if you look to this diagram, suppose there is a land use land cover in which different type of LULC classes are there, some like crop, forest, pasture, and there are different type of practices which is happening in the field of agriculture, and this is the hydrological condition, and this is the soil type. So on the basis of all these parameters, we will get certain curve number. For example, for this particular cell, we have a soil class of A, we have a row crop. So for that basis, we get the curve number at 72. And for this particular cell, we have a soil class B, and we have a LULC class of pasture. That's why we get more amount of curve number, that is 89. That means in particular cell, there will be large amount of runoff, and in this particular cell, that means 72, there will be less amount of runoff. And specifically in this particular cell, that means second row, there will be very least amount of runoff because the curve number is very less. So if your area has more than one number of curve number, then there is a concept of composite curve number. That means we get the average of all of these curve number, and we get the composite curve number 72. And if this is the composite number 72, we get the S is S98. And for respective this type of rainfall, that means if precipitation is 20 mm, then we get the runoff as 0 mm. If we get the precipitation as 50 mm, we get the runoff is as 5.1 mm. So you can see that all the things are totally depend on the curve number. So why, what is the importance of remote sensing in GIS, specifically in the SCF curve number method? So all those participants who are very much familiar with the remote sensing in GIS technology, they know that in the field of remote sensing, accessing the land use and soil map is very much easy. That using remote sensing, the land use map of the study area can be prepared. Then with the help of GIS, the soil maps either readily available or the soil testing can be prepared in the GIS domain. And then the manipulation facilities of GIS can be used to determine the curve number of each combination of land use soil classes. That means if you're in a study area of this, you have 10 number of LULC classes and 5 number of soil classes, then only with the GIS you can compute the composite curve number with very ease. Otherwise, manually, we have to, what we can say, go through lots of calculation part, and there will be error, definitely will be error will be there. But with the help of GIS, we can do some special manipulation using the land use and soil texture dataset. The next, after getting the curve number either through GIS approach or through manual approach, the next very important thing that comes in the curve number modeling is the AMC. That means antecedent moisture condition. So what is the AMC? The AMC refers to the soil moisture present in the soil profile before the start of the event. So the AMC is divided into 3 different levels. One is AMC 1, 2, 3. AMC 1 denotes that it has a dry condition. AMC 3 denotes it has a wet condition. And the higher value of the soil moisture, that means if the AMC is larger, that means the third condition, the CL will be higher. So in simple terms, AMC is nothing but the summation of previous 5 days of rainfall. Suppose if you see rainfall is falling over a ground, and if the ground is dry, so you can see that most amount of water is actually infiltrating into the ground. So that means those condition is nothing but the AMC 1. And if we see that rainfall is continuously happening from 3 to 4 days or 5 days, then most amount of water will will be a part of the runoff, because the infiltration demand will always be meet up in previous 2 or 3 days of rainfall. So in that case, we have a AMC wet condition. But in the general scenario, the ACN that we calculate from the previous formulas is denote for the AMC2. So if we get the AMC2 from the GIS analysis, we can get the CN1 or CN2. That means curve number on the basis of AMC, different AMC condition. So if we go to the varieties of literature, there are varieties of formula, and we'll get almost similar kind of value for AMC1 and AMC3 with the help of CN2 values. So presently we are using this Hawkins formula developed in 1985. So first of all, we will calculate the CN with the land use and soil combination, and after that we will calculate the CN1 and CN3 with the help of CN2. So in order to model the SCS number model, the 3 basic data sets that we require is the daily precipitation data set, the land use land cover data set, and the soil texture data set. And this is generally a flow diagram, how we can actually do the rainfall runoff modeling using SCS curve number method. First of all, we can get any type of satellite data to prepare the LULC map. Then we can get the soil data either from NBSS, LUP, or FAO, or any other agency, and prepare the hydraulic soil group map. Then we will have to get the rainfall data either from IMD or from different agency or from the ground station data, and generate the AMC dataset. And by combining all of these 3 datasets, that is LULC, HSG map, and AMC, we get the curve number for different AMC condition. Then we will get the weightage of that particular AMC, and after that we calculate the S, which depend on the CN, and ultimately we get the Q, that is rain runoff for particular watershed or particular area. Now, what is the need of actually developing the cloud-based model? Because all the things are actually happening. Everything was going fine. We get the LULC data, we get the soil data, we get the amount of runoff. But what is actually the need? Why do we need to develop any cloud-based computational model? So first of all, in any type of geospatial analysis workflow, the very first thing that we do is the data acquisition, in which we select the data, we download the data, and we download the metadata of that particular data set, so that data can be converted into required format. So then that's why the very next thing that we do is the data set preparation for a specific problem. So first of all, we identify the missing data set. We perform necessary correction like cloud computation, like cloud correction, shadows correction, atmospheric correction. Then we convert that particular data into the required format so that it can be incorporated into XYZ or any model. Then the last part that we do in any type of geospatial analysis is the data analysis. That means we convert that data into information, either with the help of some formulas, some numerical method, or some approaches. So these are the typical geospatial analysis work. And in doing all of these exercises, 80% of resources are actually invested in these 2 steps only. That means 80% amount of your computational power, your time, your data needs can be ingested in these 2 steps only, and only 20% of steps can be given to this particular, that means third task, that is data analysis. So what if all of these 2 tasks, that means 80% of workflow will get automated? That means you don't need to repeat each and every steps of this data acquisition and data preparation. So that's why we need any type of technology, or we can say a cloud-based technology, through which we set up certain rules and regulation so that we cannot repeat, or we should not repeat these 2 steps, and we can save lot amount of resources, lots amount of time, computational power, manpower, and get our data analyzed with respect to some any type of application. So that's why we had the Google Earth Engine. So what is basically Google Earth Engine? So Google Earth Engine combines a multi-petabyte catalog of satellite imageries and geospatial datasets with a planetary scale analysis capabilities, and make it available for scientists, researchers, and developers to detect changes, map trends, and quantify differences on the Earth surface. So simply, what is Earth Engine? So Earth Engine has satellite images. It has n number of satellite images, and mostly are in the public domain. And it has n number of machine learning and some advanced algorithm, or you can apply your own algorithm, and you can uh, combine these two things to get the real world applications. So you have also heard the term about the Google Earth, which is quite familiar to each of might be all of you, that what is Google Earth. Google Earth is nothing but a 3D globe visualization tool, whereas the Google Earth engine is the geospatial analysis tool. So how these two tools are very much different. The Google Earth and Earth Engine are two separate technologies focused on solving two separate problems. Google Earth is a rich 3D based map on which a raster or vector data can be overlaid, while the Google Earth Engine enables the processing of massive amount of data set of raster or vector or any other format in the geospatial field. So basically, what is Earth Engine? So Earth Engine is nothing but a remote sensing archive with a petabytes of data in one location and a cloud-based geospatial processing platform for executing large scale of data. So Google Earth has two USPs. First of all, it has vast amount of data sets related to remote sensing and GIS. Secondly, it provides you a platform so that you can process all amount of data set within few minutes of few fractions of time. So why it is such a powerful image analysis software? Because it has a wide amount of public data catalog, vast amount of public available data set, and you don't need to store the data set into your computer. Then it has a very good processing power. That means computational engine is very good. And it has very interactive development platform. Presently, it works on two libraries. One is JavaScript and other is Python, which is a very user-friendly scripting language. That means any person who is not having a background of computer science or IT can learn Python or JavaScript with very much of ease. Then not only this, but you can save and share your work routine with your colleagues or with your clients or with your students or teacher, etc. So why do we use Google Earth Engine? So because we have some advanced software like ArcGIS, QGIS, we have some good website through which we can download the data and perform our analysis. That why should we use Google Earth Engine? First of all, it has a planetary scale science. That means if you want to do anything over India and you want to apply the same technology over another part of the world, you can do with very much ease the use of Google Earth Engine. Secondly, it is a free cloud processing with the built-in functions. Thirdly, it has massive amount of online public data archive. Fourthly, you can upload your own data either from in the raster format or in the vector format to utilize the processing algorithm which are already built in the Earth Engine. Lastly, it has a flexible access through two different APIs. First is JavaScript, another is Python. So as I told you that it has a very huge amount of public data archive. It has all amount of Landsat data set from 4 to 9. 4 to 8. It has modest data set with different type of modest products are there, different type of terrain data set like SRTM, GTopo, digital elevation models are there, then n number of land use land cover are there, then various amount of atmospheric data sets are already ingested in the Earth Engine public data catalog. And this is the component of Earth Engine. So we will discuss in the hands-on session that this is the code editor. That means the main part, and it is for visualization of maps. And these are the different components, which is very useful for any type of analysis. Then I told you that there are two different APIs through which Google Earth Engine can be accessed. One is JavaScript editor and another is Python API. So both of the APIs have their pros and cons that need to be looked up. But initially, doing things in the JavaScript API is very much useful. Why? Because it has a very rich documentation and tutorials, but the Python API has very limited documentation tutorial. So if you are a newbie to the Google Earth Engine, it's my suggestion that you should go for the JavaScript code editor. And once you level up yourself in the field of Google Earth Engine, you can always switch from JavaScript to Python. You can explore more amount of data analysis or any type of analysis with the Python API. Then the very first question that comes into our mind that why, how does this Google Earth Engine or the cloud computation things work? So first of all, in the global scale algorithm processing works like, first of all, you get an image either in the form of GeoTIFF or in the form of KML, by describing some amount of bounding box, bands, resolution, you will get the image. Then you can apply any type of algorithm to that particular image. Then you can apply, you can not only get a single image, but you can get multiple image from the different collection. For example, if you want to get all the Landsat data either from 1990 to 2020 or 2021, you can get all the listed here. And if you want to filter only few amount of data set that require certain search criteria, you can do that in the Google Earth Engine. Then after that, you can apply all those all the algorithm or your required algorithm, all the data set that we have filtered. Then you can reduce your collection, either spatially reduce your data or temporarily reduce your data set. And finally, you can compute the aggregate of your particular area, of your particular field, and you can prepare some good amount of table or some interactive and good charts also. And you can perform certain types of vector operations like clipping, mosaicing, etc. Now, let me just talk about some of the few case studies that we have or I have done with the help of Google Earth Engine, and how the Google Earth Engine is very much time saving in the field of hydrology and geospatial area. For example, if I give you a task to get this particular graph from the any type of data set, that means the average annual rainfall from 1981 to 2020, and if you get the satellite precipitation data of TRMM or CHUPS, so what you will do, you will download all these TIFF file, and you will do zonal statistics of that particular area of Madhya Pradesh of any boundary, and you will align your data set in the Microsoft Excel or any spreadsheet. Then you can get this type of chart. And if you want to perform similar exercise for another state, like similar exercise for Delhi or from Andaman and Nicobar, then you have to repeat the whole procedure. But with the help of Google Earth Engine, by just typing 5 to 10 line of script, you can get this amount of information with just few seconds, not only for Madhya Pradesh, but for entire part or for entire region of this whole world. Then another case study, that if I give you a task to get the NDWI, I think most of you are very much acquainted what is NDWI, NDVI indices. So if I give you a task to calculate the NDVI of whole India using the Landsat 8, so what will your procedure? First of all, you will download the Landsat 8 of each and every corner of this country, of our country. Then you have to mosaic all the tiles, and then you will perform certain calculation like NIR minus IR upon NIR plus R. Then you will get that particular NDVI or NDWI. And in doing this, so you will get you will spend huge amount of time, you will spend huge amount of internet, because downloading huge amount of data set will be a very cumbersome issue, specifically in India. And then the software issue will definitely will be there, because most of the software, either the ArcGIS basic license version or the QGIS, will definitely hang 1 or 2 times if you want to calculate the NDVI of this large area. But with the help of Google Earth Engine and with just writing 10 to 15 line of script, you can not only get the NDWI, but n amount of indices with just few clicks and by just altering few formulas. So this is another case study that is very much helpful for the water resources and for those persons who are working in the hydrology or water resource segment. Then estimation of soil loss, that we have used the Google Earth Engine. So generally there is a model known as Raster model, and most of the hydrologists are very much aware of this model. So in this model, we get this amount of soil loss in a particular watershed or in a particular area by utilizing these 5 data sets. That means soil data, rainfall data, digital elevation model, and any satellite data for preparing the land use map. Then we'll prepare the different factors map, and we combine all these map and perform algorithm, a special algorithm, and then we get the Raster model. And for doing this task, first we have to download all these data sets, then we have to assign this prepare this factor map, and then we have to multiply all these maps to get the soil moisture. And if the similar task has to be performed from different area, then we have to perform whole this exercise from very much beginning. But with the help of Google Earth Engine, we can do this task, but just by writing few amounts of script, a few lines of a script, and by just changing the area or the year of evaluation, we can get the estimation of soil loss in the Google Earth Engine. And not only we get the result, but we can analyze those results in very beautiful manner. Either we can prepare the child a pie chart, a graph, or a line chart, or we can export our data set in the form of maps, in the form of tables, etc. So this is the task that we have done. We estimate the soil loss using the Roorkee in the Google Earth, and this thing we have done not only for Mahi Basin, for Narmada Basin, but for many basins in the central part of India. Then another study that we have performed, that estimating the surface water dynamics of Bhopal Lake, and it's a very huge lake in the Bhopal city, and we'll get the very good amount of information that how much amount of area is actually get into the water zonation from throughout the 30 years of analysis. That means how much amount of water is actually permanent water, how much amount of area is seasonal water, or the how much amount of area is actually converted from permanent water to seasonal water. So all these type of analysis have done in the Google Earth Engine itself. Then we have done land use dynamics of Bhopal city by utilizing preparing different type of land use land cover for different years, for different decades. And in order to classify those products, we have used the machine learning algorithms which are already there in the Google Earth Engine. So these are the results of that particular task. Then not only this thing, but the flood mapping. Google Earth Engine is very much useful in flood mapping because it not only supports the optical data set, but it also supports the microwave data set. And with the help of microwave data, we can actually evaluate the flood inundation map and estimate the how much amount of area actually be affected using flood. Because we know that the Sentinel-1 data is actually an open source microwave data, and all those data sets are already ingested in the Google Earth Engine catalog. Then if you are very versed with the QGIS, you can actually access the Google Earth Engine coding script within the QGIS. There is a separate plugin for Google Earth Engine QGIS, so you can install those plugin and utilize the harness the power of Google Earth Engine and the QGIS, the combination. Then as I already told you, that not in the Python API, but not in the JavaScript API, but it also works in the Python API. But for that, you should have installed any Python library into your computer or any code editor. Then this is the result of what we are actually doing today. That means rainfall runoff modeling using the SCS number method. So in this method, we have used the 3 data sets. First is soil texture data set of Open Land Map soil texture USG system. Then we have used the LULC data set of MODIS, and we have used the daily rainfall data sets of CHURBS. That means Climate Hazard Group Infrared Precipitation. So, and when we have write the script of combining this data set and calculate the global curve number and harness the global curve number maps to estimate the rainfall runoff time series for that particular area. And not only that, we have compared our the result from the ground station, that means gate discharge data, and when we have found very good interpretation in the monthly observed and computed discharge data at particular, not only Shibra, but we have performed this study in different parts of India in 3 to 4 basins. At the end of the session, I will give you a link of the paper that we have published, through which you can get the details of these models, and you can compare your result for your own area also. So the thing that I have told you in the presentation, that very good thing about the Google Earth Engine is that you are not bound to use the data set that they have provided. You can use your own data set also. For example, you are not feeling good for this modest land use. That means you are not perfectly rely on this modest land cover. Then you can prepare your own land use land cover and ingest it and use this product in the count number methodology. For example, you don't want to use the rainfall data from Chubbs. You want to use the rainfall data either from TRMM, or you want to use the rainfall runoff data from the IMD source. Then you can ingest your data in the Google Earth engine and you can utilize this product either in either with any data or for any area. So let's proceed to the hands-on session. So this is the code for which I'm going to use. First of all, I'll just open the link and show you the product that we are going to demonstrate today. So when I click the link in the PPT, my system opens this web page, and this is the Google Earth Engine platform in which the script is already there because I have saved my data set. And if I just click on the run and wait for a few seconds or few minutes, then I get it is actually generating. Then I get the rainfall runoff model for the Shipra Basin. And the result can be in the form of maps. You can see there are different type of maps, like combination of soil curve number 2 maps, S1, S2, S3 maps for different AMC, then rainfall runoff maps. Separate maps are also there, but the ultimate goal is to get the chart. And in preparing chart, it will take some few amounts of, I say, 1 or 2 minutes to get the data set into our screen. So this script has been written in over approximately 300 of lines. So at the end of this session, I'm going to share you with the script. Actually, it is already in the GitHub or in the paper, but our objective for today's session is to go each component of the script so that you will get the understanding how the Google Earth Engine and this model works to get the required amount of data set. So you can see there is a chart has been developed. I'll just click to open this chart. Now you can see this is the rainfall runoff time series from the month of January 2019 to December 2019. And in this chart, we are actually comparing the runoff rainfall in the blue line and the runoff in the red line and in the MM. And you can download this chart in the format of CSV. That means you can download the data set in the CSV. You can download the chart into PNG or SVG also. So before proceeding, there are few questions in the chat box. So if any student coordinator, if they think that the question are relevant to the session, then we can take this questions and we can proceed to the hands-on session.
Yeah, Mr. Shrikant, I think we do not really have questions. There were some queries related to the links and all, but those have been addressed. Oh, there's a question coming up. So some Anant Patel is asking, is this model in GEE is lumped or distributed or semi-distributed?
Yes. So Anant Patel, I think. Okay. So you have asked that this model is lumped, distributed, semi-distributed. So actually in this model, the curve number model is actually a semi-distributed model because here we are using the composite curve number technique. That means we are not using curve number for only specific area or not only for specific basin, but we are developing the curve number for specific each and every pixel. So like, for example, modest data set is of 500 metapixel. So that means we are getting the curve number for every 500 meter. So on that basis, we can say that yet it is a semi-distributed or very highly distributed model.
Great. Thanks, Shrikant, for answering that. If there are any other questions, please feel free to raise your hand or speak or post in the comments. We can take some questions now, or otherwise we'll proceed.
Okay.
I think there are no further questions. Probably we can
Okay.
proceed.
So we will proceed with the hands-on session. So first of all, in order to perform this modeling, the first thing that we required is we should have an access of Google Earth Engine. So I think a few of you participants have already had the Google Earth Engine account, or if you don't have it, so I'll just tell you how to create a Google Earth Engine account so that there will be very least chance of uh, getting rejection for creating, because it is up to the Google that they will allow you to open the Google Earth Engine account or not. So in order to open the account, what you will can do, I'll just open another incognito mode.
There is a question in the chat box.
Yes, you can read.
Can you please tell about calibration from Bhanu Parmar?
Okay. So yes, in the curve number method, the calibration is actually depend on the curve number, because that is the main driving factor of this whole modeling technique. So it is for calibration, you have to do the manual part. You can repeat this question at the end of the session so that I can tell you where you can actually play with the curve number to calibrate your model to get more optimum output. So I have opened the incognito mode because I don't want to I want to start freshly that how to open the Google Earth Engine account. So if you simply search for Google Earth Engine page, I think the session is recording now.
Yeah, we are recording the session.
Yes, sir.
Okay. Thank you for the response. So if you simply go to Google Earth Engine, if you simply, the very first page is the Google Earth Engine, their own page, and they have give the details that what is the Google Earth Engine and how it is very much useful in exploring the data sets and algorithm for betterment of any type of studies. Okay, so I'm not going detail into that because you can explore on your own, but the very two things which is very important is the dataset tab. So if you go to the dataset tab, you can find the enormous amount of data set that are already ingested in the Google Earth Engine platform. And not only that, they regularly keeps on updating their data venture. That means you get the satellite data from the recent part. That means if the Landsat has released the data in previously 1 week or maybe yesterday, then you can get those data set in the Google Earth Engine platform. The next important thing that is that sorry, you can, if you don't have the account, then you can go to the sign up page, and when you can go, they will ask you to sign to your Google Google account. You can give your Gmail account. So this is a sign up page, and they are asking few things. And after submitting your page, they will there is an approval process that your page will go on through, and they will analyze your inputs to let you know that you are okay for having the Google Engine account or not, because there is a very high amount of chances that they will reject your application. But it totally depends how you fill the form. First of all, you need to prepare, give your email ID and your name. The very first thing that you have to keep into your mind that you're not going to use any short form. That means if your institute needs IIT, so don't give IIT, right? Complete Indian Institute of Technology, Roorkee. Then next thing that you will do is give a proper denotation what your organization is there. For example, your organization is academia, so you will get academia, and then state. Then you have to give some small introduction that why do you want to use Earth Engine. Either you can get write in a small paragraph, or you can give in some nomenclature. For example, I'll just write hydrology, land use, land cover, bodies, or etc. You can type any of things, but please remember two things that if you select the academia, there is a very high chance of your selection, and if you select the commercial, there is a very less chance for the approval. And after submitting this page After agreeing all of these terms and technology, you will get an email that your account has been, your application has been accepted or not. So I think most of you have already opened the Google Earth Engine account. If not, that you can open by the procedure that I told you, and it may take 1 or 2 days for the Google authorities to give approval or disapproval. Okay. So after you have created your account, if your Gmail is accessible to the Google Earth Engine account, you can simply go to the Google and type code Earth Engine. Okay, so if you go to a website known as code.earthengine.google.com, you can get this page. This is the main code editor of the Google Earth Engine platform. In this, you can find the very two things, that means a script editor and the map. And in the right hand side, there are 3 tabs: script, docs, assets. And in the this is the left hand side, this is the right hand side, you can find inspector, console, and task. So if I go to my script, the model which I have, okay, sorry. So this is the link that we have set, prepare our model. Okay, so in the script segment, you can find all those scripts which you have developed by you or have been shared for you or towards you. You can find, for example, I have prepared these number of script and save, so that I can access all of this script, whether I'm using this laptop or some other PC, or if I want to share the script, I can simply go the particular script and share that particular thing. The next thing is, the third thing is assets. Asset is nothing but your own data set, which I've told you that you can always ingest your own data sets, and these data sets will be available in the asset tab. That means all these vector file and raster data sets are uploaded by me, and most of the time you will get to upload the vector data set, because for vector data analysis, Google Earth Engine is not a very good tool, but for a raster data analysis, it is a very good tool. So you need to upload your own spatial, what we can say, vector data or shapefile to get the things done. Then the very next thing, important thing, is that docs. So it has all it has all the algorithms and all the functions that are available in the Earth Engine. So we will explore this thing one by one when we are actually scripting our model. So the next thing is the when we write down our script, either we can run, we can reset the page, and we can save the script into our script tab, or we can click on this get link, so that a link will be generated. And if I share you this link, so that you can access with this code in very handy manner. After that, when I click run, so all the output that are in the map format will be displayed over here. You can find in the map, we have certain colorful map. And if we go to the layer tab, we can see there are 5 to 6 maps are there. For example, find an LULC, because we have prepared this map for this particular task. You can always check on and check off these maps. Then in the console panel, we have all amount of output that are in the format of either string or tables or chart. You can see the chart is actually displayed in the console panel. Then task is there. If you perform any task, either uploading or downloading any data set, then you can go to the task and check the status of your task. Then inspector tool. So inspector tool is nothing but if you want to inspect each and every element. For example, if I zoom to this layer and if I want to inspect this particular pixel, okay, this particular pixel, if I click on this inspector tab and I click on this particular pixel, so all the information related to this particular pixel of all these data set will be displayed over here. For example, this particular pixel have a LULC class of 12, soil class of 2, it has a curve number of 78 CN2, it has a S value of 71, 163, 30, then it has a precipitation, the latest precipitation value is 0. It has a series of precipitation, that means 365 images of a single year. That means over this pixel, these are the precipitation values in mm. Then finally, we have the runoff series for this particular pixel. But in the console panel, we are actually getting the runoff for whole this area. So similarly, you can always inspect any special rainfall and runoff for a specific pixel or for a specific area also. So this is how the whole things in the Google Earth engine works. So initially, I will try to demonstrate this model in very different segments so that you can clearly understand how the things will work. So first of all, the very first thing that we require is the shapefile of your area. So for example, if you are working in any South Indian basin or any type of basin, so you should have a shapefile, and the shapefile can be in the format of the vector data can be in the format of shapefile, KML file, GeoJSON, etc. That means the catchment boundary. So first of all, we can upload our own catchment boundary. When we go to the assets, we can click new. Okay, then the data sets can be uploaded in two format, either the GeoTIFF or the image upload, the table upload. So we'll click on the shapefile, and in order to upload the shapefile, we should have all the supporting extension. That means SHP, zip, DBF, PRJ, SHX, etc. All of the things should be there. If I go to select, this is my local directory. I will go to the. So this is my Shipra shapefile. These are all the supporting file. Either I can select all, or I can zip this folder. I can compress this folder and upload only this compressed file also. Open. So asset name is Shipra, and this is my user ID. I just simply write Shipra2 because with the name of Shipra is already uploaded. So now you can see this in the taskbar. There is a task it's actually happening. That means ingestion of table with the name projects Earth Engine Shipra2. And then we have to wait approximately 30 to 50 seconds to get our assets in the in this tab. So after this has been finished, you can check by clicking on this refresh button, and if you can find that if Shipra2 is there or not. The Shipra is my old file. It may take 1 to 2 minutes depending on the area of your catchment boundary. Okay, meanwhile, it will upload it. I'll just quickly demonstrate how we can actually use this boundary. Suppose this is the Shipra_Ujjain has already been uploaded. So if I click on this, so we can get actually this amount of properties like description, features. It has a single layer, its properties. And in order to import this data set into the script, we'll just click import. Now, after clicking import, you can see in our script editor, a table, data set with the name of table is already uploaded. Okay, so first of all, we will change this table with the name AY so that it will be easy to access or change the data set. So what we have done, we have created a separate variable with the name AY, and we have assigned the table, that means our data set. Okay, and if we click run, so nothing will be happen. If you go to the console panel, there will nothing will be print. But if I write print AOI, so what will happen? It will show me that it is a feature collection with the name Shipra_Ujjain, but nothing is actually happening over the map. That means I cannot see my shapefile. So what I will do, in order to display any type of data set, there is one thing that is map.add here. So you don't need to write all the things that script that I'm writing on the parallel mode. At the end of each section, I will share this script what I've written over in my screen. You can use this into your own screen and get the thing that how the things are actually working. So don't bother about the script. Don't try to just copy what I'm doing. Just try to understand what is actually happening behind those script. So what we have written, map at layer AY. So if I click run, so nothing will happen over here because my output will be in the format of map. So in the layer panel, I can see a layer has been generated, but I cannot see over here. Why? Because it is in the some other area, other part of the world. So what I will do, I will just zoom my layer. For that, there is a function known as map.centerObject, and I will just click AY and I will click run. Now see what will happen. It will automatically zoom to my area for which I uploaded the shapefile. Next thing, it has already, my shapefile is there and it is with the name of layer 1. Okay, I can change this name also. For example, map.add layer, I can just give this 2 bars and give any name. For example, Shipra catchment, and I click run. Now can see this. Now this layer has been with the name of Shipra. Okay, so this is how we can actually ingest our data set into our this Google Earth Engine script editor. Okay, so first of all, the very first task is to define our area. So we have defined our area. Next thing, define the period of study. So for example, okay, so we will talk about it later. So first of all, we have to define any year for which we have to get at the LULC data set. For example, we are working for the data set of 2019. So we will get the land use land cover of 2019, and we have stored the value of 2019 in the variable year. And next thing that we are doing is call the two data set. One is LULC and second is soil texture. So in order to explore the different type of data sets, we can simply use the Google. Either, for example, just simply write land use land cover Earth Engine, and we simply open the Google Earth Engine tab, and these are all the data set related to land use land cover. For example, it provides the Copernicus land use land cover for a specific area, or it will be written over here that this land use land cover belongs to the whole world or for a specific area. That means globe cover, land use land cover, and the modis will be there. The MCD12Q1 modis data set is there. So in this case, we are using the modis data set. So we'll just open this data. And this is the detail about the data sets of modis that the data set is available from 2001 to 2020. This agency is the data set provider, and this is the Earth Engine snippet through which the data set can be called. And in the description, you can see the data set, the information about the data set, and in the band, you can see the different type of bands that this data set has. That this has the LC type 1, LC type 2, LC type 3, and number of things are there. That means LC type 3 denotes the annual leaf area index. LC type 1 denotes the annual IGBP classification. And what are the classes code? If you go down, you can find this. These are the values. That means 1, 2, 3, 4, 5, 6, 7, 8 up to 17. And these are the respective classes. For example, in the map, the value 1 denotes the evergreen needler forest. The value 7 denotes open shrublands. The value 40 denotes cropland. Okay, so in order to explore this data set, if you go to the description, there will always be a sample script will be always be there for each and every data set. So if I just open this, click in this open in code editor. So this particular script, this data available with the modest data set will be displayed over here, and I just need to click the run. Now I can see the LULC map of whole world in my Google Earth Engine screen. Suppose if you want to do the LULC analysis for your area, So what you will do in traditional methodology, you will download the LULC dataset, you will create the mosaic, you will create some different, what we can say, color combination, symbology, you play with the symbology, then only you will get this map. But with just simple few lines of script, we can get this amount of data set in with just few seconds. So if you go, if you zoom into any area, okay, and if you go to the inspector task, you can click any where there. For example, if I click over this spectral pixel, so I can see this is denotes the class number 11. And if I want to see what is actually class number 11 is, I go to this page of modest dataset, I go to the band and see class number 11 denotes the permanent wetlands. And similarly, I can extract the amount of information through this tab. So what we have to do, we don't want to display all these color palettes. We just want to get our data. So either we can copy these two lines either from here, or we can simply use this line, that is Earth Engine Snap. So we'll just copy this, go to our I have opened this 2-3 times, I suppose. Okay. So what I will do, I'll just paste this, okay, and I have to give a variable name like where LULC is equal to ee.image collection model. And if I print this data, that means LULC, what I will get in the console panel, I can get there is an image collection of 20 elements, because this data set is providing LULC of 20 different years. So in order to filter from varieties of image collection to a single image, we can use a filter. So for applying filter, we just use dot filter. Open the bracket, open EE filter. And if I use control plus spacebar, I can see all the functions that are related to EE filter. So presently I'm going to use EE filter calendar range. Okay, in this function, there are asking 3 arguments: start year, end year, and field. That means start in the form of integer, and in the form of integer, and field in the form of either hour, month, year, or etc. So I want to get the LULC of 2019. So what I will do, I will just type this year, and in the brackets I will type year. And if I print run again, so now this giving me LULC of single year, that means only one element of 2019. Later on, if you can see this, the Earth Engine has two type of images. One is image collection and another is image. Image collection is nothing but when we have multiple images, then we have in the form of image collection. But when we perform, we need to get only a single image, then it is in the form of image collection. Image, not the image collection. So if you want to convert this image collection of single image into a one image, what we can do, we can apply either mean, okay, or we can write median, or we can simply write mosaic, or we just simply write first. So what it will do, first of all, it will gather all those data set with this code. Then it will filter our image with this particular year. then it will select the first image. And if I click run, so we can get this. This particular image has total 13 bands. And if I go to the page of this Earth Engine catalog, we can see there are total number of, we can see L2, 1, 2, 3, 5, total 13 bands. But we are interested only in this band, that means LC type 1. So how will do select? We will write dot select and what is the band name? It is in the commas LC underscore TYPE1. And let's see if I just, so now we have filtered our image from 20 different image collection to a single image, and from 13 different bands to a single band with the name LC type 1. Okay, and if you want to change, if I just open this image and open the band, so the band name is LC type 1. So if I want to change the name of this band, I can simply type dot rename, and I can give the band name as either LULC or other thing. For example, LULC, and I just click run. If I open this image, I can see this. Now it has only a single band with the name LULC. So presently what we are doing, we are actually demonstrating how we can access any type of data set into the Google Earth Engine. Either these data set can be in the form of rainfall, these data set can be in the form of Landsat, MODIS, or any other data set, or but presently in the format of cum number. In order to evaluate the cum number methodology, we have used the land use land cover MODIS. So we have seen the MODIS land use land cover is available from 2000 to 2020. That means 20 years of data set. We have filtered only for our respective year. We have converted this image collection into a single image. We have selected from 13 different band to a single band, and we have renamed our band name. And if I instead of print, if I just use map dot add layer and type LULC, that means variable name. If I click run, okay, now you can see this over my in the layer tab. There are two layers. There is shipwreck catchment and layer 2, and layer 2 is nothing but our land use land cover. But in the visualization, it is not looking good. So we can always change the visualization by clicking this gear sign and clicking on this stretch 100%. Because we have class range from 4 to 17, we click apply. Now we get the land use land cover in the black and white format. And if we incorporate the palette that were given in the giving in this code, if I go to the description, if I use this color palette, so we can convert this black and white image into a beautiful color. But presently we are not looking for the beautification, we are just looking for the information extraction. So if I zoom to my area, and if I want to explore the land use land cover classes of this pixel, I go to the inspector, I'll just click this, and we can see the LULC of this particular thing is LULC 10. And if I go to this tab and go to the bands, I can get the LULC 10 means it is a grassland dominated by herbivorous animals. So this is how we can actually get the data set of LULC. Similarly, we can get the data set of soil and etc. So next thing that we are going to do is actually extract the soil data set. And after that, I'm going to share this amount of code with you, and you can do on your own, and you can put your question after that. So in order to explore the soil data set, similarly, what we can do, we can simply type soil texture data earth engine. If I open the data set tagged as soil texture, so there are varieties of data, but there are really only few data set related to soil texture available for whole world or for specifically for India. Suppose these are the soil texture for Australia only, these are for the Africa only. So there is a soil data set. If I just simply type open land map. Okay, so these are few data sets like open soil bulk density, open soil clay content, open land map, USDA soil taxonomy, soil organic carbon content, soil pH, soil texture data. If I open this, so these are the agency, the dataset provider, and this is the earth index snippet. And here in this image, this is the have a resolution of 250 meters. They have 5 to 6 bands. B0 is soil texture class at 0 centimeter depth, and B200 is the soil texture class at 200 centimeter depth. So if you are looking for different soil classification for different level, you can get this data set, but the accuracy of these data set specifically in India is not very good. Why? Because these data set have been prepared with a very huge amount of ground survey, and most of the ground survey samples has been done specifically in their own region, that means European. So you cannot totally rely for the soil texture for the lower region, but for the upper region, that means at the surface, you can use this data set. And they have a different classes up to class number 12. And in the description, they have written that class number 1 denotes CL, means clay soil. Class number 5 denotes silt clay loamy, and class number 12 denotes sandy. So similarly, you can convert this classification into class A, B, C. So first of all, we will open this data set by using this. Now you will look how we can use the similar. Okay, now this is about the LULC class. Now we will open the soil data set, variable soil. We put the code what we have copied. Now this is not the image collection, this is a single image. Okay, and we have to select a single band. That means B0. And if I click print, see what will happen. The console, there is an error because it is written that B0 is not any band. If I just, it is not actually B0, it may be BO. Using some wrong phrase maybe, or simply I just copy. It is B0, but initially I was typing BO. So now you can see there is a single map, okay, of open land map. Now what we can do, we can simply click for our AY, and we can rename this data set as, sorry, we can clip this also, the LULC, and we will add map add layer soil, in which I just write as layer name as soil, and in the LULC I will write LULC. Now in the layer panel, we have three layers. One is shipwreck catchment, that means catchment boundary. We have LULC and we have soil. The color denotation is not very good. Okay, these are just in black and white color. But if I click on the spec tool and if I click anywhere on any pixel, I can found that this particular pixel has a land use land cover of 12, has soil texture of 1. So that means this area belongs to the croplands, and in the soil texture, it belongs to the clay soil. So now this information has been extracted. Now the next thing that we have to do is the convert this information into the curve number area, curve number that, if you remember in the slides, the curve number has only 4 classes. That means class number, that means class A, B, C, D. Now, presently we have a soil map. If suppose this is a raster, okay, and we have class number, we have a raster of class number with the name 1 to 12, either 1, 12, 5, 7, 8, etc. Now, what we have to do, we have to convert this raster in this format ABCD, but raster cannot be in ABCD format. That means this cannot be string. It has to be in integer or whole number. So what we are going to do, we are converting this ABCD into 1, 2, 3, 4, and the pixel is actually getting in the domain of A. That means maybe 1 or 5. We have to give the number as 1, 1. Or class number 12 is actually coming in the soil group B, then we have to denote as a 2. Class number 8 is actually coming in the soil group C, so we have to provide class number A at 3. What we have to do, we have to convert this raster into this raster. That means we have to reclassify raster into a hydrologic soil condition. And in order to do that, what we will do, there is a function in the, first of all, we will create a variable soil grp, that means soil group is equal to soil, because this is the soil, and we have to apply an expression. So now, as the spelling, this line has been converted from black to green. So that means this is an available function in the Earth Engine. And if we go to the docs and we search for the expression, so you can find the expression is in the filter, it is in the image, and it is in number. So we have to apply expression over an image. If we click open this, so the details of this particular task is written over here, that it evaluates an arithmetic expression on an image, possibly involving additional images. And how to access the different bands? You can extract the different band as B in the brackets. So let's see how it would work. So after writing soil.expression, we have to just open and close the bracket. Okay. In the inverted commas, we will write B soil greater than 10. I'll just tell you what we are actually doing. Okay. So let's just see that we are not creating any syntax error. So in the console panel, there is no error. That means there is no syntax error. So what we are actually doing? So we are saying that in the soil image, okay, we have integer values from 1 to 12. So all those integer values which is greater than 10, that means 11 and 12 will be converted into 4. And all the remaining pixels that are having value other than this condition will be converted as 0. So similarly, if I just add this map dot add layer and type file group, if I just run the script and let's see what are the different things we are actually getting. If I click anywhere on this particular pixels, any pixel. So now initially the soil class is 4, but in the final map, the soil group, this is soil class 0. Why? Because all the integers that are value other than this condition, that means less than 10, is we are denoting as 0. So what we have to do, if I just go to the soil classification, so we can see there are 12 classes. So we have to, on our hydraulic knowledge, using our hydraulic knowledge, we have to classify in different groups. For example, class number 11 and 12 will be in the soil group B. Class number 6, 7, 8, 9, and 10 will be in soil group C, and class number 1 will be in soil group A. So on that basis, we have to convert this fusion according to our own. So I'm not writing each and everything. I'm just using the already written. I'll just paste this. So now what we are actually doing, we are converting all the integer having value greater than 10 is in 4. All the pixels having value between 10 to 4 is converted into 3. All the integer that has been value from 1 to 4 will be converted into 2. And all the integer that is having the value of greater than 0 and 1, that means 1, will be converted into 1. And all the remaining pixel will be converted as 0. And if we just open, I just use this, and this time we are using soil group and run. Okay, there's an expression in because this is just soil. Now, if I click on Inspector tab and click on any pixel, I can found that the pixel value initially that has with the value of 4 now converted into 2. So this is how we can convert our soil map from their classification to our own classification. Now, the next thing that we have to do is creating the curve number map. So you know that curve number map is depend on two things. One is LULC and another is soil texture. So what we have to do, we have to create the combination of soil and LULC, and we have to give this condition. Yes, if the soil is 4 and the LULC is 12, then we have to assign a respective curve number. And if the soil is this and LULC this, then we have to assign this particular curve number. So for that basis, I'll just, because it is a very long code, I'll just copy the initial part. Paste this over here and click run. And this is the script for creating the curve number map. What we have done, we have combined the soil and LULC into a single image, and we have given the condition that if the soil is 1 and the LULC is 1, give the curve number as 35. If the soil is 2 and the curve number LULC is 8, give the curve number as 60. And in the layer panel, we can get the CN2 values, and we have the LULC, soil and LULC value. And we can inspect any of the particular pixel, like this pixel. So we can see this particular pixel has the LULC of 12 and soil is 0. That means soil may be a water body. So it has a curve number of 12. If I click on any one of the pixel over here, there the soil is LULC is 12 and soil is 2. That's why we are getting curve number as 70. So what I'm going to do, I'm just tell you how to share this code. So this is just a small segment. I'm just clicking get link. Okay, copy this link and I'm pasting this in the chat box, and you can explore up to this segment of this particular script. You just open your chat box, click on this link, and if you have Google Earth Engine account, if you have registered Google Earth Engine account, you will open. If I just copy this script, okay, so you will open this particular script into your web browser. So just check the script and see, you don't need to go line by line. You just see how the things will work. Okay, so if I need to just change the LULC year from either, for example, presently I'm using land use land cover year of 2019. I'm getting this data. So if I want to change the year to 2019 to 2005, I don't need to write each and every procedure. I don't need to download the data set. I just need to change this value from 2019 to 2005 and run this script. Now we will get the LULC of 2005. So this is how the cloud computational platform is very much useful, that you don't need to follow each and every step again and again. You can just change the variables, certain numbers, you can get your data set. So meanwhile, if there are any question, I see can check box. So I think,
I think there are a few questions.
Yes, sir.
So should we take them now, or do you want to?
Yes, we can take them now. If relevant to up to this part, I will try to answer, or if it is relevant.
There are some general questions, but I'll pick the ones which are relevant to what we discussed right now. I think there's one question by Chirag, that how one can crop their own study area, any district or any state in Google Earth Engine.
Yes. So Chirag, Google Earth Engine doesn't provide any vector data set, or is very, very few data, but few of the user worldwide has ingested their own data set. So there is a data set known as GAUL. In the end, I'm going to share the link how to extract those data set, but it is an international boundary which is not accepted to Indians. That means it is a incorrectly showing some international boundaries. So it is my advice, don't use that. What you can do, if you are having your own shape file, either for your catchment area or for your district or for your state, you can incorporate in those things. But it is all about the administrative boundaries. But if you are using any hydrological boundary, either the catchment, basin, then you have to delineate on your own, either in the QGIS or ArcGIS or any other platform, and you can import those boundaries into the Earth Engine.
Perfect. I hope the question is answered, Chirag. Thank you, Shrikant. There is one more question by Pavan, who asked that how can we see yearly change in LULC?
Yes. So if you want to just see the LULC change, you can change this value like 2005 to 2015, and you can separately visualize the data. But if you want to analyze the how much amount of classes has been converted from this class to that class, so for that purpose, you need to write a code, a separate code of zonal statistics in the Earth Engine. I will tell you in detail at the end of the session, because at the end of the session, we are preparing actually a chart. So what this chart is actually doing, it is computing the average rainfall and average runoff for your area. So you can use those similar charts for land use only. So for that purpose, you can create two charts, one from 2005 LULC and from 2015 LULC. I hope You get things clear?
Yeah, we got thank you from Pavan and Chirag. I think their questions are answered. So I think that's all. There are a couple of questions which are general in nature, so we'll take probably them
We will take in the end if
at
it
the
is
end.
general.
Yes.
Okay.
Excuse me, sir. Can I ask a question?
Yes, sure, Gagandeep, please proceed.
Yeah. Sukant, I was curious about the script which you just shared. So I just changed the area of interest with my shape file for Alaknanda watershed.
Okay.
Okay. So when once the script was run, so I was just checking the CN values. So
Okay.
I just observed that in the snow-covered areas, the CN value is displaying as 100.
Okay.
But this is like I was also curious about what to take I was preparing this map for my own study before this. So
Okay.
I always have a doubt what CN should we assign for snow areas, and I could not find a proper explanation in the literature also. So I just want to know
Yes.
how did you like using your script,
Yes.
why
Yes.
it is showing 100.
So Gagandeep, thank you for putting this question, because there is a negative side of come number technique is that it is not advisable for snow area.
Yes.
Because I have used many of the script literatures, so there is no definite CN number for snow area. But if somehow you define some curve number of snow area, either nearby 100 or nearby 0, but the conversion of that snowfall into the runoff will be inaccurate. Why? Because converting snowfall into runoff will depend on several factors, not only on the rainfall. It will depend on the temperature, it will depend on the radiation, inward and outward radiation. So that is why curve number technique totally depends on the rainfall, LULC and soil. So that's why for hilly, for snowy part, curve number model is not suggested. So that's why you won't get easily the curve number of snow area. But if some literature is there in which the conversion of curve number runoff will be used as an input to some other model for a snow watershed, you can use that.
Okay. And one more thing I want to ask, like if for a snow-covered watershed, if we want to neglect those areas or ignore those areas, so what change should we make in the code? Like because we don't have a proper CN values for this area.
Yes. So what you can do, yes. So if you go to this code and if you suppose the LULC 16 is snow cover.
Yes.
What you can do, either you can incorporate the LULC 16 as 0.
Okay.
Or 100. But please remember that if you go to 0, then the composite curve number will be fall down.
Yes.
And if you do the 100, the composite curve number will give a higher value. Right. Okay. So what you can do, you can simply try, you can perform some hit and trial that in the soil expression code, you want to exclude. There is a command known as GET. If you go GET or greater than, I'm forgetting actually. Wait a minute. Okay. So there is a command GT in the image collection and in the image, which will tell you through which you can tell the system that take only those pixels which having value greater than this or lower than this. So what will do? It will mosaic out all those unwanted pixels. After that, you can perform the LULC classification.
Okay.
Okay.
Thank you.
So we can proceed further.
Yeah, if you
minutes are left.
Few questions, we have the questions, but I would
sir, actually, I mean, in by this code we can incorporate the temperature data.
So the curve number doesn't incorporate the temperature into their formula, but if you come up any new literature which is utilizing the temperature incorporating in with the LULC and soil, you can always have the temperature data, because Earth Engine have lots of temperature data maximum like GLDS, FLDS, and other data. NOAA data set is also there. You can utilize those data set also.
Because I mean here in I'm staying in Punjab, so here there will be some amount of snow cover. I mean, if temperature decreases, then we can consider it as a snowfall. Temperature increases, then it's considered as snow runoff, like that.
So it is my personal advice as a hydrologist that if you are using any doing modeling for a snow cover area,
Yeah. I mean, we are doing.
right, then don't use the curve number method. Either use some what we can say physical balance approach, either from Wick model, SWOT model, or maybe HMS is there. So you have to go with some advanced model, or the snow fed model is there, snow mod model is there. You can go with that model, not the curve number model.
Okay, it is curve number model. I mean, only based upon the curve number, right?
Yes, it is only based on the curve number.
Okay, sir. Okay.
You can explore anything, because see, either if you are adopting any type of model, any type of equation, you will require certain type of inputs. If you are able to incorporate those equations in the Earth Engine, you can develop your own model. That means a cloud-based model. So presently, I've developed the curve number model because it is the very simplistic approach. If you come up very new algorithm, you can incorporate your own in the Earth Engine. Because all you need is the data set and the formula, nothing. So we will just quickly go to the next part of the session. That means now we have created the curve number map. Now the next thing that we have to look is the antecedent moisture condition. So what is actually antecedent moisture condition? That I've told you that if the rainfall is having certain amount of rainfall is there from past 13 days or from past from past 5 days, if a certain amount of rainfall is there, then it is come under the AMC1, AMC2 and AMC3. Okay, and if the AMC is changing from 2 to 3 or 2 to 1, then the curve number, corresponding curve number will change. And for that purpose, first of all, we have to analyze the rainfall data set. So if you go to the Google again and search for precipitation in Google Earth Engine. Okay. So you can get n amount of maybe 6 to 7 type of data set which is useful for rainfall. So presently I have used a CHURBS data set, CHURBS daily. Okay, CHURBS daily is available, CHURBS Pentat is available. If you click on this CHURBS daily data set, it provides the rainfall in mm, the daily rainfall, and you can access this code. Or if you want to access for a particular, so I'll just open this data set. Okay, and this is mine. So I have actually utilizing the data set from 1st of May 2018 to 3rd of May 2018. So May 2018. Can you hold for a 1 minute? I just
Yeah, sure. I think that would be fine.
so sorry for the glitch. So here we can write the date, either we can write the date here, or we can actually define the date initially in the initial part of the code. So for example, if we have defined the period of study at start date 2019 and end date 2020. So we can use this variable into our rainfall data set. Start date, and we will put the start date over here, and we will put date over here. Sorry. Yeah. And if I just print this data set, and let's see what is actually happened in the console panel. So now they have printed 365 image. Why? Because it is a daily data set and we are actually utilizing 365 images. So now after that, we have to calculate the AMC condition. So for that purpose, we are actually using the loop. So if you are utilizing, have you used some programming language like Python and Java, so you have come up with a term loop. But in the Earth Engine JavaScript, in their documents, they have generally suggested that don't use the loop, because loop will actually will result in hanging your code and will not properly work can be done. So what we can do in order to achieve this thing, we have to convert the image collection. Okay, we have to convert this image collection into the list of images, and we can apply the functions. If I open the previous code, so after that, these are the rainfall data. What we are going to do, we are going to convert the image collection to the list of images, because converting from image collect to list of images, we can actually access the previous 5-day images also. And after that, we have create an algorithm through which, if the image, that sum of that particular image is lesser than 13, if I open this, if that's lesser than 13, then it will take AMC condition 1. If it is between 13 mm to 28 mm, it will take as AMC condition 2. And if it is more than 28 mm, then it will take AMC condition 3. And after the 3 MC condition, we will get the 3 curve number, and the curve number 2 and curve number 3 will be depend on the curve number 2 value. So we have create the curve number 1 and curve number 3, and accordingly we have created S image for first curve number, S image for second curve number, and S image for third curve number. And after utilizing all of this information, we have get the final runoff. That means what we have done, we have defined a function that if S image 2, if AMC is less than 13, then it will use S image 1, and if it is greater than 28, it will utilize the S image 3. And afterward, we have created the chart which I was telling you. See, I'm not going in every very detail of this code, because it will take a huge week, a whole week, in defining each and every what we can say, what we have done, because I have taken more than 10 days to develop. So, but you can get very much insight of all the things that we have done here. So after getting the image collection of this rainfall runoff, we have created a chart. That means which utilize that UI.chart.image series and convert the image collection into the spatial mean and provide the chart into this particular format. So as I told you that each and every detail could not be tell, but I'm just going to share this code with you just by clicking this. Sorry. Get link, copy, and I'm pasting this in the chat box. So you can access this code, and what you can do, simply you can change your study period, either 2019, 2020, or from 2005 to 2006. But please make sure that it should not be more than 2 years, because it will certainly hang. That means it will take 2 to 3 minutes, or more than 2 to 3 minutes in generating the result. What you can do, you can create 2 years. If you want to model for 10 years, you can run the model 5 times for 2 years, and you can combine those data set into Excel or any other spreadsheet. And if I just open this into the new tab, and if I download the CSV, and open the CSV into the Microsoft Excel or in any other spreadsheet format. So we get the, in the one column, we get the date in this format, January 1, 2019. Then we got the precipitation in the mm. Then we got the runoff in the mm. And you can plot the graph over here also. And you can.
Shrikant, you are only sharing this Chrome window. So
Okay. Sorry, sir. Okay. Thank you, sir.
It's fine.
Okay, so after opening the CSV file, you can see in the one column we have got the date, in the one column we have got the precipitation, and in the third column we have got the rainfall. So if you download two years separately, you can just combine those data set either upward and downward, and you can plot the chart here also. And you can utilize this runoff in some other software or in other modeling techniques to perform this calculation. So you can access this code by this link also, or you can access by the GitHub link because it is already published. So if you go to the github.com/Sukhant Jain, so you can get not only this, but if you open the repository of Google Earth Engine, so I have put only few of the codes, like if you go to the JavaScript, like actual rain average. So in the PPT, I have shown you how to get the average amount of annual average precipitation for whole area. You can open this, use this script. You can use the curve number model, which I've shown you now. You can perform the zonal stats, which a participant was asking about the land use land cover change pattern. You can use this. And if you are very much familiar with the Python, you can go to the Python API, and I have written few of the script of zonal statics and other things, which you can access with this also. And a paper in the current science, I think a link has been shared to you also. If not, I will try to. So the details of this model can be you can find out in this link also. You can explore this, and if you found any encounter any problem, or it is my advice or my suggestion that you should do modeling for your own area, and you can compare the result with a GND side data set or with the compare with other model, because I've compared this model with a sort output or with the GND side data, and it is giving quite good result for the monthly, not for the daily, because curve number application does not apply the routing techniques. So that's why on the monthly basis, on the smaller watershed, it is giving the good result. So I think this is from my side of this whole curve number technology. So if are any doubts, any question?
Yeah, Shrikant, so I think we have 2-3 questions that we left.
Yes.
And there are a few more questions coming in. So I'll go with the very first question, which was asked by Ashu Chaudhary, who asked that what is the resolution/area pixel we get the optimum information to? No, I'm not very sure what it means. Ashu, are you there? If you can.
Yeah, hello. Thank you, Shuk. It's very nice presentation. I'm actually very new to this field, but I understood most of the things. So my question was very basic, that when you start analyzing, you need to think about what pixel size you are targeting. So how Google Earth gives us like the optimum information about.
Yes.
Yeah, so please.
I got your question. So see, as I told you that Google Earth is just a platform. Okay, it doesn't provide you their own data set. It will provide you modest data set. It will provide you Landsat data set. It will provide you Sentinel-1 data set. Okay. So whatever resolution the data set that we have, present the free and open source Sentinel data is the optimum resolution, like 10-meter resolution is here. So if you use those data set in preparing the LULC, you will get the 10-meter resolution result. But if you use the model data set, which I've used in my present case, you will get the 500-meter resolution. So it is totally different. Suppose if you have your own data set of Cartosat of maybe 1 or 2 meter, you can ingest your own data set into the Earth Engine and you can apply your model there also. So it is dependent on the data set which you are using.
So the follow-up question is that, okay, we have some data from the Google Earth Engine, and if we have some data from our own field study, or so to say, some relevant articles, so can we club the two data and like?
Yes, you can club it.
Okay. So in order to formulate that, we need to formulate it in the format of Google Earth Engine.
Yes, yes.
Kind of data
The
set.
Google Earth Engine supports only two data sets, raster and vector. Raster in the form of image collection or image. So you can ingest your image either in the TIFF format, or if you have multiple images, you can create the image collection and ingest in that.
So in order to do that, do I need to have more information about this image, the resolution, the image studies, the
No. You don't need to have very detailed knowledge of image classification. You just need to know about your own data. That's it.
Okay.
The only thing here, you have a plenty information about your own data.
Okay. Thank you so much. Thank you.
Great. Thank you, Ashu, and thank you, Shrikant. So Shrikant, we'll go to the next question, which is by
Yes.
Patel, who is asking that can we add our soil texture image as a raster file and then extract the curve number from it? Is it possible or not?
Yes. You can extract, you can
if they want to use their own soil texture image.
Yes, you can add your own and you can convert the curve number according to that only.
So there's a question by Nitin Singh, who is asking that in the PPT you had shown the number of formulas for CN number curve number conversion from 2 to 3 and 2 to 1. Can you throw some light how these formulas were developed based on the antecedent moisture condition, and are these formula empirical? I think which is very basic. Nitin, you can find the answer to this question in any of the hydrology books, but still, if
yes,
you want
you have said right that it is a very basic thing that if you go to the very basic book of Subramaniam of hydrology, so they have a very detailed description on how the antecedent moisture condition is actually affecting the runoff in the curve number method, and how we can use the AMC condition in defining different curve number. Suppose if we have AMC, very dry AMC, then of course the curve number has to be on the lower side. So on the different, as I told you in the PPT, that not only one, but the different researchers have come up with the different formulas for AMC 1 and 3. So you can apply or you can hit and trial for your own area, but the most widely used is the formula which has I have shown you. I don't remember its name.
These are basically empirical formulas which are available almost in all the engineering hydrology books. So
the Hawkins is generally used formula which is found in the Subramaniam book, but the related research has been developed on a certain area. So you can explore your own area research publications and you can do the analysis on that area also.
Perfect. Thank you, Shrikant. We have one interesting question from Pawan, who is asking that how can we represent the spatial change in precipitation or LULC along with the temporal change in one TIFF file? So we want to show temporal as well as spatial changes in either precipitation or LULC, but in one single TIFF file.
Okay, so I'll just show you the code. So if you want to prepare a map of a maybe precipitation, so either it has to be a single tip precipitation or a sum of precipitation. Okay, so what you can do, I'll just now you can see that I have prepared this search here. Okay, so here you can see this. We have added 3 maps. One is rainfall runoff. One is rainfall runoff selecting the precipitation, and we have used the sum. So what we are doing, we are displaying the map of sum map. Okay, so if you want to see the change in the sum map, what you can do, there is an option of the slider change. That means you can actually slide this map and see the change detection. But it is not as visible for the rainfall runoff modeling. Why? Because we actually see the temporal variation. But still, if you want to go for the spatial variation, what you can do, you can create your sun map for your area and you can change the palettes. For example, I have used the palettes PPT with this one, in which the maximum value is 0 and the minimum maximum value is 2000 and the minimum value is 0. So that's why it is producing this type of result. But if I narrow down this pixels minimum maximum, what we can do, we can analyze more effectively how the things the values are changing from different area. Or the third thing you can do, you can download this TIFF file into your local drive, and you can always explore the special what we can say prepare a nice map and publish in your report or etc. I think
yes, Sushant, I think that was wonderful, your answer.
it was.
I think this reminded me of one work which I did a couple of years back using Google Earth Engine, and I'll quickly share it with the participants so that they can see what there are different things that we can Google Earth Engine. Let me quickly share my screen. Shukant, so this will stop your screen, so just give me a minute.
Okay, no problem.
You can share
Okay.
back. So this is right. I hope you can see my screen right. So Google Earth Engine also allows you to make something called apps. They call it Earth Engine apps, which can be integrated in any website or with any of the different tools, online tools which are available. And there sliders that Shukant was just talking about, that we can add these sliders wherein we can change the dates, we can change the time, and then we can show different rasters. So here what we did, we created this one soil moisture forecasting tool, which was for some Middle East part and some parts of the South Asia. And in the backend, we had a deep learning code which was working, which was making predictions, forecasts of soil moisture over next 16 days. And those were automatically shown over this Google Earth Engine app. So we have this tab on the left-hand side panel, they call it panel, which shows the values of soil moisture, latitude, longitude of a selected point on this map. It also further shows the time series of the soil moisture at that particular point. And as you see, I clicked on a different point and it started generating the map for that different point. And then there is legend, which shows this color schemes, and further you can choose different rasters from here. There are different options which you can select. For example, right now I selected root mean square error, so now it is showing the root mean square error for that particular day based on the forecast that we had. And then from this time slider, I can change the dates. Although this code is very long, you can try some other day, but the main advantage that we have, that we can integrate this with some other website. For example, this is a Google website where we integrated this code. Now you will not look at what we wrote, but you will simply see this, which will be updated automatically every day. And then by just scrolling here like a Google map, you can show your results. You can show the forecast. In this case, we were showing the forecast. You can also integrate these charts, which can be exported, as Shukant told us. We can export it to CSV. We can further add different elements. For example, here we are, I think, showing the values of root mean square at different points. If we click somewhere at some other point, it will update it. So those kind of things are also possible with Google Earth Engine, and I would encourage all the participants to explore it further, because this is a kind of new revolution in this field where we can use Google's resources, their storage, their computation, and we can produce these kind of tools which will be very helpful. So coming back to the question and answer, Shukant, we have a couple of more questions. There's one question by Anand, who is asking that, is it possible to develop distributed rainfall runoff model or only semi-distributed models?
So as I told you that it is actually preparing the curve number on the pixel basis. So in Hindi, इससे ज़्यादा क्या लोगे? Because all the models that we have, that either in HackHMS, so what it is doing, it is basically deriving the curve number on the sub-basins. SWOT model is also doing that thing. Also in the WIC model, we are actually preparing the grid of maybe 1 kilometer or 2 kilometer. Not lesser than that will be creating some problem in developing the model. So I don't think so there is anything which provide the curve number, the model with at the pixel level, and it is totally depend on the user data set. If you use the Sentinel data, you will get the curve number at the 10-meter resolution. So you can get the curve number at that level also. Totally depend on the whatever the data you are using actually.
Great. So there's another question which is by Ganga Nagri, who asked that my study area is less. I mean, I think he's referring to that his study area is small. So he is unable to classify LULC using Google Earth Engine. So is there any method to do this classification for smaller areas?
Yes, there is very good and very advanced machine learning algorithms are there to classify your study area. And if your study area is small, you can use the Sentinel-2 data set, which has a 10-meter resolution. You can create your own classes, but you have to define your own training data sets, and you can use those classified products into your Earth Engine, hydrological model.
And there was a hand raised. Sorry, I missed it, and then now I cannot see who was it. So if there is someone who wants to interact with Shukrant, please go ahead. Okay, so we have another question, Shukrant, from Bhanu Parmar, who is asking that can we use station data?
Yes, Bhanu, you can use the station rainfall data into the Earth Engine, but the conversion from station, the Excel data into the raster data is quite cumbersome, because you have to convert first into the NetCDF format, then in the NetCDF format, you have to convert the GeoTIFF, then in the GeoTIFF, the 365 GeoTIFF for a single year. So you have to create n number of GeoTIFF, then only you can upload. But the good thing is that if you are able to explore the Python API of the Earth Engine, then it is going to be very easy for you. Just you have to convert the curve number and bring that into your local GeoPandas data frame, and you can call the Excel file of the station data, and you can club those two data sets into your local machine, and then the thing is going to be very much easy. That's why I told you at the presentation that as for a starter, you have to stick into the JavaScript. But once you get very much familiar with the Earth Engine, the data sets, then you can easily switch to the Python. And once you switch to the Python, a new varieties of scope or new scope of things will be open for you. I think I answered the question according to my updated knowledge.
Yeah, I think that is great. And I see we have one more question coming in from Anant. Anant, do you want to ask it yourself, or do you want me to read it out?
Hello.
Yes,
Hello.
Anant.
Yeah, I'm asking that can we use Google Earth Engine for prediction of LULC change for future based on the past history of LULC or based on changes?
Yes, Anand, presently I don't know about any algorithm that do this task. But I think there is a model, I don't remember its name, which do this task on a desktop. This is a desktop-based model, which incorporates the older LULC and gives the newer LULC, the prediction LULC. And if you are able to incorporate the equations of those model into the Earth Engine, then only you can do this. Or if in fact you can use some machine learning algorithms are there to give the historical time series of LULC as an inputs and get the latest time series. But I don't know how the things will work. But you have to go to some what we can say, to some literature that someone has done it. But yes, if the equation is there, if the algorithm is there, then you can develop your own.
Okay, thank you so much.
Thank you, Shukrant. And yes, I think Gagandeep has mentioned in the chat, Markov chain modeling is one of the ways in which we can do the LULC prediction. And I think there are many other well-established methods nowadays which can be used for LULC prediction. The question is that whether we can do that on Google Earth Engine or not would obviously depend on your coding skills and the capabilities that Google Earth Engine offers. So I think we do not have any further questions, and we are already 20 minutes past our scheduled time. So we'll stop here. And I would again thank Shukant, thank you very much for your valuable time for this great hands-on and the demonstration on Google Earth Engine. And I'm sure it will be very helpful for all the student participants in their research work. Google Earth Engine has already provided us a lot of data sets which we cannot download on our computers, but there you can analyze terabytes of data sets without having to download even single megabyte of data onto your computer. So I'm sure your talk and demonstration will be very much helpful to the students. One thing I want to ask, we had many questions in the chat regarding sharing of this recording. So if it is fine with you, can we provide the recording of this session to the participants?
Yes, there's no problem for my side. You can share this, or in fact,
I think you have already shared your code, which is wonderful. I think.
Yes, you get the code is available in the public domain. The good thing about this Earth Engine is that most of the developer are actually sharing their research work in the open source domain. So yes, most of my works are in the open source domain. You can access my GitHub account, and through GitHub account, you can get to my YouTube channel, through which there are some tutorials related to QGIS and Google Earth Engine. You can always access this, and I will try to share this this recording to all the participants also, or the Anirudh, the coordinator, will be sharing the video.
Yeah, so Anirudh can interact with you later on, and then we can discuss on how to share. Yes. In the meanwhile, I just pasted the link to Shukant's GitHub page, so participants can visit that page and they can look at all the public domain codes which are shared by Shukant, and probably they can use them and they can interact further with Shukant.
And you can suggest to improve. All the participants are requested to suggest me that how the open source sharing platform can be improved, so that more followers will be there.
Yeah.
I would like to thank the Pravaaah team, Dr. Ashutosh, and all the student coordinator and HOD for organizing this event, because it is very much useful to use this technology, and the participant has to understand the Google Earth Engine is just a tool, and it has to be linked to your imagination. It has to be linked to your own perseverance, how to utilize this tool in exploring n number of things.
Yeah, so as Sushant mentioned, there are many possibilities. Even many of the things on Google Earth Engine are not fully explored yet. So there's a lot of possibility that students can do many innovative projects, utilize different kind of data sets, integrate them, and make the apps. That Google Earth Engine app that I showed you, that was one very small example, but people have developed very advanced apps on Google Earth Engine which can enable a lot of things, especially in terms of real-time predictions of the thing, real-time forecast of the different hydrological variables. And that would be something probably after this hands-on, we'll see many of our students using these tools for their projects. So with this, I think we have reached at the end of day one of this Pravaaha, wherein we had two wonderful workshops today. In the morning, we had a workshop on TU flow, and now we had this wonderful talk as well as a hands-on session by Shukant on Google Earth Engine. So I think we can now conclude. Professor Brijesh, if you want to add some concluding remarks, that would be wonderful. I think Professor Brijesh might be away. So with this word, I want to thank all the participants, all the speakers, especially Shukant and the Pravaaha team who worked really hard to make this possible, and all the participants who took time to be here with us and to take part in this. If you have any suggestions for us, or if you have any other queries coming later into your mind, please feel free to write to the Pravaaha team or to me. We will try to make sure that we address all of your concerns and try to improve these sessions in the future. Also, we have 2 more days of this Pravaaha. Please visit Pravaaha website if you are interested in any of the competitions that are going on tomorrow. Feel free to participate. We would highly encourage all of you to participate and be there with us in remaining 2 days of the Pravaaha. So with this, I think we can close day one. Thank you very much, Shukant. Again, it was wonderful to have you here.
Thank you too also.
So I'll stop.